Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. I'm also the program leader for the Physics with Astrophysics program, which you can see here. If you go onto the website, you can see more information about it. Now, the idea of this video here is to give a sample lecture which will be a part of that particular program. It's also part of the normal physics program because this one is going to be a first year module and all physics students will cover this module. But if you're doing the astrophysics one, then you actually will end up doing more specialist astrophysics ones, which I've done sample lectures on as well. So this one here is essentially going to focus on the HR diagram. It's not going to be the first lecture, it's going to be one as you've kind of got into it a little bit, and we're going to have a look at stars. So this particular module is called Introduction to Modern Astronomy, and the idea here is that you cover pretty much all areas of astronomy, astrophysics, a little bit of cosmology in your first year. You learn the fundamental concepts, and then if you're doing the astrophysics route, so the physics with astrophysics, then what you do is you do more specialist modules in your second and third and even fourth year if you decide to do a fourth year. You can also do your project work that are more astrophysics related, but if you don't do the astrophysics, you still do this module and you basically get an overview of all the ideas and concepts in astronomy and astrophysics. And this goes all the way from planets, how planets form, to how the universe as a whole behaves, and we end with kind of like the fate of the universe and things like that. So this particular one is going to be around about midway. We've got about 30 or so lectures on this particular module. This one's going to be lecture 12. Now at this point here we would have done the planets and we would be then moving on to our stars, and we're going to have a look at the HR diagram or the Hertzsprung-Russell diagram. And in astrophysics this is going to be one of the key fundamental plots or relationships for stars that can help us understand how they form and lots of other information about them. So this lecture here, this video, is going to focus on introducing the HR diagram so you've got a good understanding of it. So when you go and learn about stars, it makes a little bit more sense. So what is the HR diagram or the Hertzsprung-Russell diagram? Now it can be displayed in a variety of different ways, but it is essentially an experimental. It's from experimental data. It's not from theory. It's from observations of stars. And it's a scatter plot showing the relationship between things like the star's absolute magnitude. That's how bright a star is from a set distance. Essentially, its luminosity and its effective temperature, so how hot it is. But you may find that along the bottom you've got temperature. You could have spectral class, because spectral class relates to temperature. And then on the kind of vertical axis, it could be luminosity, essentially how bright the star is, or it might be given in absolute magnitude. It depends really, but they're both kind of, they all work essentially. And on the right, the left-hand side, you can see that both are denoted, and that's quite common as well. So when you take measurements of lots of different stars, you start to get this sort of pattern. It's not random. You can see that there actually are groups there, and that's really useful for understanding stellar evolution, things like that. So, zoomed in a little bit more, you can see it in a bit more detail here. So again, along the bottom you've got your surface temperature or the spectral classification, because they basically go hand in hand, and then you've got your absolute magnitude and then your luminosity. And you can see you've got certain groups labelled on there. You've got white dwarfs, you've got the sun denoted on there, you've got giants, main sequence, supergiants, all those sort of things there. And it's also done in colour as well. So spectral class and temperature also relates to temperature. So on the right hand side you've got your cooler stars, they're redder. The ones on the opposite side, the left hand side, are hotter, they're bluer. So that's basically the layout. As you go up on the plot, they get brighter, more luminous. So where did it all start? Well, it was kind of in 1911, Danish astronomer. I'm not going to pronounce his first name, I'll get it wrong. So Hertzsprung here was plotting the absolute magnitude of stars against their colour, which is essentially, again, their effective temperature. And he got that plot on the right hand side there. So, back then we didn't have measurements of lots and lots of stars. So he started to make those measurements and started to build up this sort of plot. This is the start of it essentially. And that's the original plot that was published in 1914 in the Nature journal, basically. So it all started kind of here. However, he wasn't alone. And actually, quite a lot of the time in science, we often don't talk to one another as scientists. We do our own work. And it just so happens that another scientist is working on exactly the same idea, and then you go to publish and present your results at the same time. And this is kind of what happened here. So there was an American astronomer here, so Henry Norris Russell, independently did exactly the same thing. So he was plotting the spectral class against absolute magnitude of stars, and he produced pretty much the same sort of looking plot because he was doing the same work. And again, this plot was originally published in the Nature journal in 1914, which you can see there, and they're quite similar. So similar sorts of amounts of stars, similar sort of idea, and also they're coming to kind of the same sort of conclusions as well, because they've drawn those kind of trend lines on there. So they're getting the same sort of patterns, even if they're not doing the exact same amount of stars or the exact same stars. So what happens then when they start to do more and more of these stars? Well, both of these are showing a relationship between the temperature and the luminosity. So if we have got the temperature along the bottom and then luminosity along the vertical axis, what that's telling you is that cooler stars are less bright. That kind of makes sense, really. And actually, what you can see in that center part, that diagonal line, that's then going to be known as our main sequence. That's stars that are in the main part of their evolution or life, I suppose, where they are fusing hydrogen in their, or hydrogen into helium in their cores, and that's known as the main sequence. And a lot of stars sit there. You then have that relationship between temperature and luminosity. The other groups, it changes. And when you learn more about stars and stellar evolution, you'll understand why they come off that main sequence. And again, this is really useful for understanding stellar evolution. So you've got the original plot by Hertzsprung on the left, and then the original plot by Russell on the right-hand side. And you can see they share similarities there, basically. So yeah, as you start to add more and more stars, then you get quite distinct groups. It's not random. So you can see here we've got things like giant stars. So you've got that main sequence I just mentioned, and the size of the star relates to its luminosity, its surface temperature, when it's on the main sequence. A more massive star can gravitationally, I suppose, collapse or compress the core further than a lighter star. That causes higher temperatures, it can generate more energy, it becomes brighter. So that's what happened on the main sequence. But with the red giant one, they actually stop fusing hydrogen in their core, and it changes the way they transport and generate energy. And that's why they actually swell up and become cooler. You've then got your white dwarfs down the bottom. They're very small, but very hot. Because they're small, they're actually not very luminous, despite being very hot. So you've got all of these interesting groups that then kind of start to stand out the more stars you add onto this particular plot. So if we go to the actual plot again, as I mentioned, your hotter stars are going to be on your upper left. This is relating to the actual main sequence though, because actually white dwarf stars are very hot. So we could just say that actually they're over on the left. So hotter stars are on the left, cooler stars are going to be on the right, regardless of their size. So supergiants can be massive and red dwarfs can be really little, but they can have the same surface temperature. So cool stars are on the right, same again with your hot stars. It's kind of independent of their size at this point. If you add the size in, that gives you their kind of location luminosity wise. Now you can get the actual temperature by using Wien's law. So if you take the spectrum of light given off by a star, what you actually get here is something that looks like, well, you can see the spectrum of those plots for different temperatures. So the green one there is peaking around about 5,500 Kelvin. Now if you know the temperature, well, not the temperature, let's go back again. If you know the wavelength where it's actually peaking, so that green one kind of goes up and then comes back down. Where it's at its highest, its peak, it's the energy density is the highest. You then trace it down and look at the wavelength, and it's approximately 500 nanometers here. you can then use Wien's law, the equation for that, to work out the temperature. So that's how you actually get the temperature, to plot it on these plots here. So you use some nice physics known as Wien's law. So, as I just mentioned, your hotter stars are going to be peaking at shorter wavelengths, although actually I didn't mention that, to be fair. Just to note again what Wien's law is, this relates the relationship between the temperature of a black body and the wavelength in which it emits most light. So a hotter one is going to peak at the shorter wavelengths, they're higher energies. So a green star here is going to be further to the left on a shorter wavelength where it's peaking, where most of its energy is going to be. A cooler star is going to be towards the redder part of the spectrum. And that essentially kind of gives you your colour as well. And if you want to calculate that, you can use this fairly simple equation here. So your lambda max is your peak wavelength, and I've actually inaccurately labelled the wrong one here. I've actually labelled the temperature as opposed to the peak wavelength. It should be the lambda max. So here for the green one at least, we would put in, let's say 500 nanometers, and we'd use our constant of proportionality, and we'd rearrange for T, and that would give us our temperature, and it should come out at around 5,000 Kelvin-ish, thereabouts really. So it's quite easy and straightforward to calculate the temperature here. So once you've then got temperature and you've got the spectrum of a star, you can also give it a spectral classification, and you're probably going to come across these, and they're not in a nice alphabetical order. So it goes O, B, A, F, G, K, M. So O is going to be your hottest, bluest stars. M-class stars are going to be your red, cool stars, like your red dwarfs, your red giants, things like that. So you can get it directly from the temperature, their apparent colour, but also you can look at features in their spectrum. So how strong their hydrogen lines are, so like the Balmer series, are they deep, are they not, and other notable features. So for example, very hot stars, like O-class stars, these have ionized helium lines, whereas the very cool stars, they're actually cool enough to have molecular lines in their spectrum. They can actually support those. So you get things like titanium oxide lines, which you'd only get in those very cool stars. So actually it's a collection of all of those things there that can help give you your spectral class. So you can have a spectral class, temperature on the HR diagram, depends, or you have both basically. So back to luminosity then, just to define really what it is. It's the total amount of electromagnetic energy emitted per unit of time. So it's essentially the flow of energy from the surface of the star. The more energy that's emitted per unit of time, the higher the luminosity of that star. And quite often your units of luminosity are going to be in watts. So how do we then calculate the luminosity? We can use this equation here. So your luminosity then is basically going to equal 4 pi times the radius of the star squared times the Stefan Boltzmann constant times the temperature to the 4th power. Now we've already got the temperature of the star. We would then basically need to find its radius, which we can do using a different method here. Now the bigger stars are going to be more luminous. So irrespective of temperature, if they've got the same temperature, so let's take two stars here. We've got a main sequence star that's around 30,000 Kelvin and a white dwarf star that has the same surface temperature. The only difference between those two in this equation here is the R, is the radius. Now you can see straight away, if you have a smaller star, they're going to be significantly less luminous. So it's basically relating to this radius squared, really. And if we actually include temperature there, so if we actually had the same size stars, so if they were the same size but they were different temperatures, then that would make it less luminous. So hotter stars are going to be more luminous, cooler stars are going to be less luminous. And actually this is going to be a much stronger response to the temperature than the radius because it's to the 4th power. And you can see on the main sequence there that as we reduce the temperature, then we reduce the luminosity. as well. So we can see on the right hand side, at the bottom, you've got your red dwarf stars. They are significantly less luminous than your hottest stars right at the top on the left hand side. Now, we can actually convert between luminosity and absolute magnitude. So the absolute magnitude is just essentially a magnitude of the star, how bright the star is, from some set distance, so a standard distance from that. But we can also convert to a luminosity, and again, on the HR diagram, sometimes it's in absolute magnitude or it's in luminosity. So your absolute magnitude here is your capital M, and if we want to convert between the two, there's actually a few different ways you can do this, because it depends if it's like the bolometric magnitude, which is the magnitude across the full spectrum or on a certain filter. But anyway, this will give you a good starting point nonetheless. We've got the luminosity of the sun in watts. So if you see that symbol, which is the circle with a dot in, that means it's a solar unit. And we might have it in radius or mass. In this case here, it's luminosity. So that's the luminosity of the sun in watts. And if we then multiply that by 10 to the power, and then in brackets you've got 4.83 minus the absolute magnitude of the star, divide by 2.5, we then get the luminosity of the star, and that can basically be interchanged. So if you want to convert between the two, that's one way of doing it. And if you want to do the other way around, then just essentially rearrange it. So then, on the main sequence, and I've highlighted that with the green box around the diagonal part labelled main sequence, they do have a mass luminosity relationship. So the mass of the star is proportional to the luminosity to some power n. Now actually, it's not a constant relationship, and you can probably see the most obvious bit here is if you get down towards the red dwarf stars on the lower right, it kind of curves down a bit. Now the reason for that is the stars on the main sequence, they're not transporting their energy from their core, where it's made, to their surface in the same way. There's different physics occurring there. Now red dwarf stars are predominantly convection. The way that their energy gets from the centre to the surface is convection. But it switches over as they get more massive, and that changes the luminosity, because if you think about what luminosity is, it's the rate of energy passing through, or being emitted from the star. So if you're changing the mechanism and how it's being transported, you're going to change the luminosity. So that relationship changes depending on its actual mass, but there is a relationship nonetheless. A more massive star is going to be more luminous, and you can see that here. So more massive stars sit at the upper left, less massive stars at the lower, or the bottom right, I should say. So these stars here are in hydrostatic equilibrium. What that means is that they're generating energy in their core by fusing hydrogen into helium, and the gravitational forces that are trying to collapse them are balanced by outward radiative pressure. So they're in this equilibrium point. They're generating enough energy that there's a radiation pressure that's balancing them against gravitational collapse. And they can sit there until that ceases to occur. So if they stop fusing hydrogen, they would no longer be in hydrostatic equilibrium. But on the main sequence, all of the stars are in this particular process here. Now, red giant stars sit towards the upper right on the HR diagram, so they kind of come off the main sequence to the upper right. So more massive stars are going to sit at the top of this, less massive stars at the bottom, although that's not necessarily the case, because when we start to do red giant stars, they go through a bit of a sequence actually, and it's not necessarily to do with the mass, it's to do with their internal energy process, and they will actually kind of go over the top as they become a planetary nebula and then a white dwarf. But a more massive star is going to be more luminous, so it kind of makes sense, at least in the basic terms. So what happens here is the stars move off the main sequence because they've run out of hydrogen in their core. So when they stop fusing hydrogen in their core, they actually, if they're big enough, will fuse helium in their core. They collapse further, that generates greater heat, so they actually generate more outward radiative pressure because there's more energy being created. Because the gravitational force hasn't changed, but you've increased the outward force, it causes them to swell up. And if they get bigger, they increase their luminosity, which is why they go up on the HR diagram. But because they also swell up, their surface temperature decreases. They get cooler temperature because their surface area increases massively. So this is basically what happens here. You then end up with this helium core. Now, again, it depends on the actual mass of the star, whether you actually get helium fusion or not. But for the Sun, you won't. It'll just be an inert helium core. Now, what happens then is this is no longer in hydrostatic equilibrium. Your outward pressure is going to be greater now than it was before, and that pushes it further out. And the reason why it does this is that helium core collapses because there's nothing holding it out anymore, and it heats up lots. You then get hydrogen surrounding it being drawn in. That goes into this new hotter area because it's heated up. That then starts to fuse into helium, and because that shell around the helium core now has a bigger volume, it can now create a bigger outward radiative pressure. And that's basically what happens for red giant stars. But when we go through the red giants, we're going to touch on that in a lot more detail and see exactly why that occurs. So here you've basically got that shell of hydrogen, has a greater volume, as I just mentioned, and that's why they technically swell up. Now, the bigger stars, you actually get a whole load of layers occurring for bigger, or not bigger, but heavier elements. And they actually start to have an interesting effect and can relate to things like pulsating variable stars. But again, that's a topic for other lectures. So what happens now, once it's kind of coming to its end of the red giant phase, it starts to lose the outer layers because it can kind of, somewhere around there is where you're going to get your variable stars, where they kind of pulsate, they get bigger, and they kind of expand and decrease. And over time, these strong stellar winds involved with these particular stars as well, they lose their outer layers, and it starts to expose the very, very hot core. So because of that, they've got these really expanded outer layers, which makes the actual object itself appear very big. So remember luminosity, they become quite luminous, and they start to expose the hot core, which is very, very hot. That then means on the HR diagram, they're going to go over the top there. Now I'm going to come back to planetary nebulas in a little while, but this is the evolutionary phase kind of as a solar mass sort of star, sun-like star essentially. Now, once it's done that, it's lost its outer layers, and you're just left with that internal core. It's no longer fusing any elements at all anymore. It's completely ceased. There's no fuel left for it. It's just a collapsed core. That then ends up as our white dwarf. So it comes down again into the white dwarf group here. Now, because it's not generating any energy anymore, it's going to cool down essentially. So it will start out on the upper left of the white dwarf group, so hot and luminous, and then over time it's going to slowly cool down, and it's going to work its way down to the bottom end of the white dwarf group, and then give it enough time, it's going to end up as a red dwarf, but not the same as a main sequence red dwarf, because it's going to keep cooling and keep cooling, but that will take an enormous amount of time, and then it will eventually just cool down until it's not emitting in the optical part of the spectrum anymore. So these are no longer in hydrostatic equilibrium. There's no outward radiative pressure anymore. They just collapse. So they're not generating any energy, and that's why they're really, really small. And when we say small, these, well, they go from like the size of the sun to the size of a terrestrial planet like Earth. So that's a huge decrease in their radius, but their surface temperatures are very, very hot, a lot hotter than the star would have been originally, but they've lost their outer layers. So the evolution on that main sequence depends kind of on their mass. So you've got the main sequence there, which is kind of like the main black line. You've then got these blue lines, which represent the pre-main sequence of stars. So this is as they're forming, and then when they make it onto the main sequence, that's their track they make to it, is the blue line. And then the red lines are ages, essentially, so where they are on their age. And what you'll notice is that the smaller mass stars, so the actual number, the blue number here, is their mass in solar units. So 1 is the same as the Sun. 0.1 is 10% the mass of the Sun. You can see they drop down vertically, whereas the bigger stars go more horizontally. So that's a key thing in understanding stellar evolution. And again, when we come to look at star formation in more detail, we're kind of going to understand why that occurs, why some of them, the smaller ones, drop down, whereas the more massive stars track horizontally instead. And when we then look at the actual movement of stars off the main sequence into red giants, and now they're finished on the main sequence, they then go into the red giant phase. Again, they take similar sorts of tracks. What you find is that the smaller mass stars, or the lower mass stars, take a more vertical route, whereas your massive stars take a more horizontal one. And the reason for that is that we're going to come across something like the I forget now what this is called, but it's basically going to be a maximum luminosity, or it's the Eddington limit. This is the maximum luminosity a star can actually get, and if you get it any more luminous than this, it blows its outer layers apart. So some of these massive stars, they can't become any more luminous, because if they did, they would overcome their gravitational force and they actually would blow their outer layers apart. So they move horizontally, they don't become any more luminous. Whereas the smaller ones, they swell up a lot more. They can become a lot more luminous, so they actually go vertically. But also, their energy transport mechanism is different. They have convective cores for bigger ones and radiative cores for smaller ones. And red dwarf stars don't go into red giant stars because they're fully convective. Again, we'll look at that when we look at red giant stars. So we're just going to kind of finish this off with some objects or stars that don't appear on the HR diagram. So we've got red giants, supergiants, main sequence stars, red dwarfs, white dwarfs, but there's a number of stars and objects that don't appear on this HR diagram, and we'll explain why. So neutron stars don't appear on the HR diagram. Why is that? Well, neutron stars are the end point of more massive stars than the Sun. So a solar-like star, like the Sun, that's going to become a white dwarf, which is the size of Earth, or thereabouts. It's terrestrial rocky planet size. A more massive star has more mass. It can collapse its core even more, and it actually collapses down to about the size of a city. It's about 20 kilometers. That means that your radius in your luminosity equation here is very, very small. They might be very hot, so they could be, hundreds of thousands of Kelvin surface temperature, but they are incredibly small. And because of this, they have extreme properties that can't be plotted on the HR diagram. So they have very hot temperatures that can't be plotted, but it also affects their luminosity as well. They're not actually very luminous because they're incredibly small despite being very hot. Pulsars are actually pretty much the same thing as the neutron star. So we can see the pulsars, but we don't really plot them on the HR diagram for the same reason. Very hot, but also very small. In fact, pulsars are neutron stars. So, same reason. We then also got your supernova remnants. This is the Crab Nebula here, and this is what's left over from the end point of a very massive star. In the centre of that, you've got a neutron star, but the outer layers that were blown off during the supernova is what we can see here. Now, these don't appear on the HR diagram because, again, they can be very hot, but it's also their size. These are very large, and these will be on the order of light years in size. So it gives them extremely high luminosity because they're so big. So these don't appear on the HR diagram. Plus the HR diagrams for the stars. This is technically not a star. We've then got your planetary nebula, same reason for the supernova remnant. This is the smaller stars that don't go supernova, but they lose their outer layers. These are very high luminosity again, because they're very, very large. So they could have radiuses on the order of light years, and the central stars can be very hot as well. So due to extreme properties, they're not really going to fall on the HR diagram. Plus, again, they're not really a star. The central point is a star, but the wider object is not. We've then also got black holes. Now, this is the image of a supermassive black hole, but it's not, because we've never imaged a black hole and you never will be able to. It's actually the disk around it that we can see. So black holes don't give off any light, so we can't plot them on the HR diagram. They don't have they do technically have a temperature, but it'd be quite low. And they have very small sizes if you want to take into consideration their Schwarzschild radius or their kind of event horizons, things like that. But these don't appear on the HR diagram either, and that's an image of one with the accretion disk around it, but not the black hole. So thank you for watching.